This is section 5.4, part B, sum and difference identities. Sum and difference identities can be used to rewrite trigonometric expressions as algebraic expressions. So we need to write the sine of arctangent radical 3 plus arcsine of x as an algebraic expression of x that does not involve a trigonometric expression. Now before we expand these, this is the same thing as saying the sine of alpha plus beta. Now we're going to think of alpha and beta as two different triangles. Our alpha angle, let's put in the bottom corner, and our beta angle will also go in the bottom corner. Now tangent, if you remember, is opposite over adjacent. Arctangent is the same thing as the tangent inverse. And radical 3 we can write as radical 3 over 1. So this is our opposite side. This is our adjacent side. So if this is my angle, my opposite side goes here. My adjacent side is down here. We can do Pythagorean theorem to find the length of the third side. The side across from the 90 is always your C because it is your hypotenuse. When you square root, it cancels. To get the C by itself, we do take the square root. When you take the square root, it can be positive or negative. But since we're talking about a length, this will be positive. So we know the length of this third side is going to be a positive 2. We can do the same thing with our beta. This is the arcsine of x, or the sine inverse of x. And we can write x as x over 1. Remember, sine is opposite over hypotenuse. So my opposite side is going to be x. My hypotenuse side is going to be 1. We need to find the adjacent side. So once again, we can use the Pythagorean theorem. And we can say x squared plus b squared is equal to 1 squared. Or x squared plus b squared is equal to 1. We want to get the b by itself, so we're going to subtract the x squared from both sides. Right now we have b squared, so we are going to take the square root of both sides. So we know b is going to equal the square root of 1 minus x squared. So because we did decide this is a sine sum problem, we know the sine of alpha plus beta is equal to sine of alpha plus beta, sine of alpha cosine of beta plus cosine of alpha sine of beta. So if we plug in our values, this is going to give us the sine of the tangent inverse of radical 3 times the cosine of the sine inverse of x plus the cosine of the tangent inverse of radical 3 times the sine of the sine inverse of x. Now the stuff's in the parentheses is just telling us which triangle that we're looking at. So we're going to look at our alpha triangle first, and we're going to find the sine of our alpha triangle. Remember, sine is opposite over hypotenuse. My opposite side is radical 3, and my hypotenuse side is 2. Now I'm going to look at the cosine of beta. So we look at our beta triangle. We're going to find the cosine of it. Remember, cosine is adjacent, which is radical 1 minus x squared, over the hypotenuse, which is 1. Now we're going to look at the cosine of the alpha triangle. Cosine is adjacent over hypotenuse. And then we're going to look at the sine of the beta triangle. Sine is opposite over hypotenuse. Now let's simplify. Remember, when you have radical times a radical, you multiply the stuff that's inside. Radical 3 times 1 is 3. Radical 3 times radical negative x squared is going to be negative 3x squared. 2 times 1 is going to give us 2. 1 times x is going to give us x. 2 times 1 is 2. If we combine these, this is going to give us, because the denominators are the same, x plus the square root of 3 minus 3x squared all over 2. Now this is written without any trigonometric expressions. Now we're going to start verifying, again, like we were verifying in section 5.2, but this is verifying with sum and difference formulas. Now this is the sign of a difference problem. Remember, the sine of alpha minus beta is equal to the sine of alpha cosine of beta minus the cosine of alpha sine of beta. The first value is your alpha, the second is your beta. So if we substitute these in, we're going to have the sine of pi over 2 times the cosine of x minus the cosine of pi over 2 sine of x. Now remember, sine is your y-coordinate on your unit circle. So if we look at the y-coordinate at pi over 2, we will have 1. Cosine of x is just cosine x minus the cosine at pi over 2. The cosine is your x-coordinate, and the x-coordinate at pi over 2 is 0 times the sine of x. 0 times anything is 0. 1 times 1 is just the value itself. So this is equal to cosine of x, which is what we were trying to verify. Sum and difference identities can be used to rewrite trigonometric expressions in which one of the angles is a multiple of 90 or pi over 2 radians. The resulting identity is called a reduction identity because it reduces the complexity of the expression. So this is an example of a reduction identity, but we just need to verify that this reduction identity is actually true. So we're going to start just by doing the same thing we were doing before. We're going to see if it's a sum or difference. This is a sum of sines, so we're going to start with that formula. Remember, your first value is your alpha, the second one is your beta. So if we plug in our alpha and beta, we're going to be left with sine of theta times cosine of 3 pi over 2 plus the cosine of theta times the sine of 3 pi over 2. Now if we simplify these, sine of theta is just sine theta times the cosine of 3 pi over 2. The cosine is the x-coordinate, and the x-coordinate at 3 pi over 2 is 0. Cosine of theta is just cosine theta. Sine of 3 pi over 2, the sine is the y-coordinate 3 pi over 2, which is a negative 1. So when we simplify, we're just going to be left with negative cosine of theta. Let's verify this reduction identity. Same thing again, this is tangent and it is a difference. So we're going to use our tangent difference identity. So if we substitute in our values, we're going to have the tangent of x minus the tangent of 180 over 1 plus the tangent of x, tangent of 180. Now the tangent of x is just the tangent of x. The tangent of 180, remember tangent is y over x. The y-coordinate at 180 degrees is negative 1. Is 0. The x-coordinate is negative 1. So down here we're still going to have 0 over negative 1. Tangent of x minus 0, because 0 divided by negative 1 is just 0, will just give us tangent of x. Tangent of x times 0 over negative 1 will just be 0. 1 plus 0 is 1. And anything divided by 1 is just itself, so this will just equal the tangent of x. You can solve trigonometric equations using the sum and difference identities and the same techniques that you used in lesson 5.3. So we're going to find the solution of cosine pi over 3 plus x plus cosine of pi over 3 minus x is equal to 1/2. And we're going to just look at the interval from 0 to 2 pi. So if you notice, we have a cosine sum and we have a cosine difference. We're going to break both of those down first. So if we look at the first part, the cosine of pi over 3 plus x, that's going to become the cosine of pi over 3 cosine of x minus the sine of pi over 3 sine of x. Then we're going to do the same thing with our cosine of alpha minus beta. Now we're just going to go through and we're going to find the values that we can. So on our unit circle, the cosine of pi over 3, or the x-coordinate of pi over 3, is 1/2. The sine, or the y-coordinate, is radical 3 over 2. Now you do need to check the sign in the middle. This is a positive value. We are going to distribute it to both pieces, but because it's positive, it's not going to change anything. And then we can write everything out and combine like terms. So 1/2 cosine plus 1/2 cosine is just going to give us 1 cosine, or cosine x, negative radical 3 over 2 sine of x, plus radical 3 over 2 sine of x will just cancel. So we're just left with cosine of x is equal to 1/2. Now we need to get the x by itself. We're going to take the inverse cosine. You're going to look at your unit circle. You're going to find me the x coordinates on your unit circle that are 1/2, and that's going to be located at pi over 3, and x is equal to 5 pi over 3.